you must have heard by now that Internet of Things is very hot. And we are actually already in the middle of it by having covered Bluetooth. But now today we officially start that. Internet of Things and wireless protocols for IoT. IoT is Internet of Things. And the first protocol that actually is the basis of many things going on in IoT is 15.4. So we talk about that totally in this lecture. And in that, there are several new 5 concepts that come in. Those we will talk about. And then enhancements. So this lecture is all about 15.4. So right now, we see Internet all around us. But if you count, it's only 1%. 99% of the things are not connected, such as your refrigerator, car, washing machine, heater, access, AC, garage. This should all be connected. Anything that you touch, deal with, has to be remotely accessible. And so the internet industry, the networking industry, believes that from 10 billion today to 50 billion. And in 2020, and so there is a big market and big demand and big activity in this area. 14 trillion projected market, and so we have already seen the mobile revolution. Now people believe it will be IoT revolution. Now there are other names for it. Cisco calls it Internet of Everything. Okay, so they just don't want to include them. I mean, basically, for them, some things that are not even touchable should be part of this, and so everything. A smarter planet is what is called by IBM, and the word is smart. You saw last time we said why they changed from Bluetooth LE to Bluetooth Smart. You will see a lot of smart things around nowadays because of the smart grid and things like that. Okay, so everything is becoming smarter, and which means connected to the internet. Industrial internet, cyber physical systems, and then another popular name for this is Internet of European Things, for those among us in the networking community in the United States. So actually what happened was Internet of Things, the research started basically in Europe. And I remember 5 years ago when we were doing next generation here in the United States, well, 5 years means 2005, 8 years ago, they were talking about Internet of Things over there, and we said, oh, who cares? Okay, so it has come out true actually. It turns out that they hit on the right thing at that time, and so, I mean, we called it the Internet of European Things, but I think now we are serious about it. Anyway, so there are lots of protocols happening on IoT. The first thing is 11. A lot of devices which are connected to the internet use 11 as such because it is so cheap, because it is there everywhere, and so on and so forth. Particularly in many applications, you don't have to use cell batteries, and so that's good enough. And Bluetooth and Bluetooth Smart is the next thing which we have talked about. So those two we don't need to. Third thing I need to talk about is Zigbee, and Zigbee Smart. You see, smart again. So Zigbee Smart, when I need to talk about Zigbee Smart, I need 15.4 because half of Zigbee is 15.4. Then there is something called 15.6, which is body area networking. Wireless HART. Actually, the name is very confusing. Highway Addressable Remote Transducer Protocol looks like something to do with transportation. It has nothing to do with transportation. It is just a historical name, and now they don't even spell it out completely because that is really confusing. But HART is a very common protocol which is used in industrial automation. And then ISA, Industrial Automation Society, has its own standards, Z-Wave, MyWi, N+, Wireless M-Bus, and there are other variations of these such as XB. So there are plenty of wireless activity related to IoT. And then there are plenty of activity, networking related activity without wireless. So even the wired protocol, people want to do IoT. So power line communications, you can connect your refrigerator clearly with a power plug to the internet as well. Sixth low PAN, which is the networking layer. Routing protocol for low power and low noise is another protocol which is being done at the routing layer. HC-M2M architecture, and the list goes on. You don't have to remember these names, but this I put it together so that we can figure out which are the most important things to talk about. Okay. So on to 802.15.4. So 802.15.4 is the key lower layer protocol, Phi and MAC protocol, that is used by many IoT protocols. At least 5 are shown here. ZigBee runs on 15.4, 6 low PAN runs on 15.4, wireless HART runs on 15.4, MyWi runs on that, and ISA runs on that. So 15.4 is the key. So what is 15.4? 15.4 is officially called low rate wireless personal area network. So 15 has many committees, and we saw the whole list in the previous lectures. 15.4 is the low rate one, the one that doesn't really care for the throughput, it just cares for the connectivity. As long as I can send a message in an hour or 1 hour or 1 second or 1 minute, that's good enough. We are not talking milliseconds and microseconds. In some cases, probably we are, so we'll see that too. But the rate is important, low rate. And now there are many bands it runs on, but 2.4 gigahertz is most common. And if you remember, 2.4 gigahertz is about 79-80 megahertz. So that is divided into 16 5 megahertz channel. Okay. And it uses one channel, just like Wi-Fi. So here is one more thing you will notice. 15.4 comes from 802, right? Which the same people go to the next room and they are meeting in 802.11. And when they get bored, they come to 802.15. So there is so much commonality between 15 and 11. Okay. And so actually I'm going to skip one line. For example, it says that they use direct sequence spread spectrum, DSS. If you remember that, you just take a code and then for every 0 and 1, you use that code. That was the original 11. Right? CSMA CA you have heard of before in 11, that is here. Back off, exponential back off is here. Beacons are here. Coordinator. There is no access point. Just like Bluetooth. There is no access point, but there is a coordinator. At least Bluetooth is totally peer-to-peer, but here it is coordinator. Well, Bluetooth is not peer-to-peer, sorry. Bluetooth had a master. So here is a coordinator where, some device can become a master. We call them coordinator here. All right, going back to the line that I skipped, 250 kilobits you get at the phi rate. So when we say 250 kilobits, it's like 56 kilobits for G and A. By the time you get to the top, you lose a lot. So here you lose and you get about 50 kilobits for the applications. And since really it is not the bits which count, it's the symbols which counts as to how much power you spend, the symbol rate is low. And symbol rate is, if your bit rate you want to keep high and the symbol rate low, means you have to have multiple bits per symbol. Right? And if you have multiple bits per symbol, that means you'll have to have multi-level coding. And so that's what we use. I mean, we would love to have 256 QAM, right? That is multi-level coding. However, that is too expensive, I mean, for these little devices. So they go up to not 256, they just go up to QPSK. Just basically 4 levels. So 4 bits per symbol. We'll see as to how that becomes basically QPSK in a minute. And then low rate, short distance, and the distance is small. So they are not planning to go kilometers, they're planning to go 10 meters. And that means low power and low energy. And since the number is so large, we said 50 billion, we know that we will run out of 48-bit addresses. We haven't, but we will not run out of it. So what they did and what they do is they use 64-bit addresses. Alright, how do you get 64-bit addresses? Well, if you have your 24-bit OUI, just put 40 bits behind it rather than 24 bits behind it. So you have your, you go to IEEE and you get a 22-bit OUI. And if you want to use it for 11, you just put 24-bit behind it, make a 48-bit address. If you want to use it for 15, you put 40-bit behind it, and you get a 64-bit address. Now you can have lots of things that you can address in your chips. I mean, your chip can be used. All right. So this is called Extended Unique ID, or EUI 64. Obviously, 64 is the wrong direction to go when you have only 256 kilobits. So this has to be compressed, and then we'll see this is compressed into 16-bit. Now, why not 3 bits? Because 3-bit is too small for IoT. Right? In your body, you probably have more than 7 things. And so 16-bit is big enough to cover the interesting number of devices that you want to put into one network. And at least, and it's not too big to be put into these little, devices. All right. And the protocol is very simple, no segmentation, no reassembly. Maximum frame size is only 127 bytes. So that 127 bytes, by the time you put all the headers together, leaves only 77 bytes. A little bit more sometimes. All right, this is just an overview. I'm going to go through the whole lecture today in detail about all this. Any question at this point? Okay, the topologies are something that we have seen before, are very similar. So star topology is clearly allowed, but it also allows mesh. And before I go any further, notice that there are 2 kinds of devices, full function devices and reduced function devices. Full function devices are a little bit more expensive because they have a little bit more logic. They can become a coordinator. Reduced function devices are cheap. They don't have that much logic. They cannot become a coordinator. All right. So that's the main function, is that FFD and RFDs. And it doesn't have to be a star. So you could have devices which are hanging off. And third thing is that you don't really have to go through the coordinator for all the communication. Coordinator does coordinate the communication, but you can talk in parallel. So if A wants to talk to B, it can talk directly. All right, the coordinator. So FFDs. FFDs can become coordinator, can also route messages to other nodes. RFDs cannot become coordinator, but can only be a leaf. So you could have a very complex diagram, and the reduced function devices will always be the leaf. FFDs that start a pan become the coordinator. So now here's the thing. In this room, for example, you might have lots of devices which could have potentially this, and there could be a lot of FFDs. And so any one FFD could say, well, I want to start a network, and then becomes the coordinator, and everybody else compatible with that could join. If they're not compatible, they start their own network. For example, if there are 2 people, my body devices will join my network, your body devices will join your network. So there can be multiple networks in the same area, and the devices join it, and any FFD can start it. In the star topology, all communication is to and from the coordinator, which is by design. So if this is the topology, I mean, everybody talks to the coordinator. But if the topology is on the right side, then that is not a star. In P2P topology, FFDs can communicate directly. Each piconet has a PAN ID and is called a cluster. So that's another name now. So this is a cluster on the left, and a cluster on the right. And so basically a cluster could be a star or a mesh, but you could combine many clusters together. Before I come to that, a node joins a cluster by sending association request. This is very similar to 11. The PAN coordinator says, I am here, and then you say, okay, can I join you? And then when you don't need it, you disconnect. And once you join, you get a 16-bit address for that particular instance. And when you communicate, you can use either 16-bit or 64-bit address. Okay? All right. So the topology continues by having not just a single cluster, but you could have multiple clusters. So here is a cluster. There is another, this is a cluster, but the restriction here is that the whole thing has to be a tree. Right? And so this is actually the whole network. Even though it is a cluster, it is a clustered tree. There are no loops. And so there are some holes in the protocol because, for example, the protocol doesn't really specify how do you ensure that this is a tree. So there is no spanning tree protocol or something like that. Okay? There is no protocol which tells you how to route messages from here to there. You have to figure it out. So that's why there are so many other protocols which do that for you, the higher layer protocols. Like these, they cover the routing. Okay? 15.4 allows you to have a network which is bigger than what it can basically write the protocols for, in some sense. All right. And this picture, which actually came from the standard directly, the latest version of it, 15.4, shows that there are some RFDs which are routing, which seems to me, again, either an oversight or maybe RFDs are supposed to know routing as well. Okay, so this is not a mistake, but I didn't want to correct it. I saw this in the diagram and I said, okay. All right, so much about the topology. Now we go into the MAC and the PHY. MAC has two modes. The first is the beacon-enabled mode and with CSMA-CA. So beacons come every so often, which is a long time. And then if the beacons come, then there is a slot. So there is a fixed time interval which is given. Some of these slots may be reserved, so that is contention-free period. And some of these slots are available for contention, so that is called contention access period. Now, some of you know the difference between Aloha and slotted Aloha. Anybody knows the difference between Aloha and slotted Aloha? Yeah?
Aloha, the slotted Aloha has to start at a particular slot.
Yeah.
But Aloha can
start anytime. So what is the advantage of slotted Aloha?
You know when a transmission ends, so you know when to start.
Yeah, right. But the thing is, here's a summary. That's good. Excellent. Basically, the idea is that slotted Aloha is better than Aloha. Aloha is simply, you can just say whenever you want. You don't look at you don't even do carrier sense. You just say. So, slotted Aloha idea, this was the second protocol after Aloha was done. Aloha was the first wireless protocol in some sense, okay, wireless networking protocol. The second one was slotted Aloha because they realized that if we don't allow people to just speak whenever they want, just at particular time, then the efficiency goes up by a factor of 2. So this is slotted CSMA-CA. Now CS increases the efficiency significantly again. So you think carrier sense is better than Aloha. So the carrier sense it increases it, but slotted carrier sense is even better than carrier sense. Okay, in terms of collision probability or losing. Anyway, so this is slotted Aloha. So you can see 16 slots, 0 through 15, and then there is a lot of inactive period, a lot of time when everybody is sleeping, including the coordinator. Okay. Now, not everybody is awake during the activity period. Coordinator has to probably be awake, but I think basically coordinator can announce the beacon and then get off, I suppose. But then in the GTS, for example, it is allotted. It is already. Oh, sorry. I think coordinator has to be awake because the GTS is guaranteed period, and it could be given to a particular node, and the nodes can request it from the coordinator saying that I need, every cycle 2 slots, or every 2 cycles 1 slot, whatever you need. So any of those frames coming in from 0 through 10 could be to the coordinator, right? So in fact, I suppose everybody probably has to listen there. No, not everybody has to listen, because all other frames are going to the coordinator anyway, because in many cases, in most cases. All right, other than in direct to direct. Okay, so the idea is that this is very similar to what we saw in 802.11 in some sense, and except that there was not inactive period in 802.11. Here there is a big inactive period. And what else? Everything else is very similar now. Okay, so next mode is beaconless. So beacons are optional. And if you don't have beacons, then you have unslotted CMA, which means that you can start anytime you want. There's no time boundary. And then every frame can be either acknowledged or unacknowledged. So acknowledgement is optional. If you need the acknowledgement, then the acknowledgement will be sent very soon after the frame, and it is not required to CMA. This is already guaranteed. So when you get the frame transmission, after that, basically you can just continue the acknowledgement. And however, after the acknowledgement, people have to wait. And this is a little complication that they have put here, is that they have CIFs, just like before, short interframe spacing. However, they also have LIFs, long interframe spacing. If it is a long frame, then you have to wait longer. If it is a short frame, you have to wait shorter. So they have 2 wait intervals. All right. And I'm not really sure as to why. But let's see. The TAC is actually shorter than the CIFs. So if you remember, in the case of 11, you had to wait 1 CIF and then you send the ACK. Right? Here, actually, there are 3 interframe spacing. One is the ACK spacing, and then there is a CIF, and then there is a LIF. If there is no ACK, then you only have LIFs and CIFs. Okay? So basically, the reason all this works very well is because this duty cycle, as they call it, is very low. Duty cycle means the busyness, the utilization. We are expecting here the utilization to be 1%. 99% of the time people are sleeping. Right? We are not talking about very busy 802.11, which actually it is. Here it is, people just sleep most of the time. They wake up once in a while and then say hello and then go back to sleep. All right? So in that environment, you can just wake up anytime and say something, and so that's the environment it is designed for. Now, this philosophy is totally opposite of the Bluetooth philosophy. Now, you notice the Bluetooth was a very different access method. They didn't believe in CSMA and all that. So here it is all 11 philosophy. All right. So you basically, the normal CSMA, you wait until the channel is free. Once the channel is free, then you draw a random number, and If the channel is still free, then you transmit. If the channel is busy, then you draw another number and you go up by a factor of 2, but you don't go up to 2 raised to 16 or 10. You don't need that much. You just wait for 2 raised to 2 maybe maximum. So you stop at 2 raised to 2. And because the reason you don't want to wait too long is because when you want to transmit, you want to keep your electric circuit up, and you don't want to wait too long. So you just draw another small back off. Acknowledgements or beacons are sent without CSMA CA. So when the beacons are coming, they don't look at the medium. They just send the beacon. The acknowledgement, the same thing. You send them without a beacon. Without a CSMA. Any question about the MAC part? Is it making sense? Okay. The frame format is straightforward. Actually, all I wanted to show here was one little bit here, but let me just see. So there are several fields such as frame control, sequence number, PAN ID, destination address, source ID, source address, auxiliary header, security header, payload, and FCS. So the key thing to notice is that your address consists of at least 32 bits. You have to have a 16-bit PAN ID, which network you belong to, and 16-bit in that PAN that has been assigned to you, right? So either you could do that, or you could give your whole 64-bit address. So basically the address fields, it could be 0, 16, or 64. Okay, bit. The PAN ID could be 0 or 16 bits. Source ID same way, 0 or 16 bits, and source. So basically, in many situations, you don't need to know the address. You know why? Because it is guaranteed. Those GTS slots, we know where it is coming from. Of course, we have given it to X, and Y can speak, and that will happen later on, but right now it doesn't. And so basically, in some situations, we know the source and the destinations, and we don't have to put it in the packet, and we are just going to save some energy. All right. So the address can be 0-bit, PAN ID can be 0-bit, then security can be there or not there, depending upon how strong security you want. You can have 0 through 70 bits. So there are lots of variability here, right? Then we go into frame control. Frame control has the usual stuff such as frame type, and there are many different types. Whether there is security. Frame pending is more bit. Basically, it says that I am sending you this, but I have more. So don't go to sleep. Okay. ACK required. This is the bit that tells you that you have to acknowledge it after you get the packet right away. So this is optional. If it is 0, then you won't get the acknowledgement, and you are happy and they are happy, right? PAN ID compression is basically this PAN ID we have we have taken it out. 16-bit is the PAN ID, but I have taken it out 1 bit. So basically this will become 0-bit here. Destination address mode. The destination mode is one of these 4 possibilities. It is PAN ID and address not present, not present. And then 16-bit sort address, 64-bit extended address. So you put that bit here, and then that many bits you count when you come to that field. Okay, so this frame control is in the beginning. And here, if these 2 bits say that it is 64-bit address, so when you come to the destination address field, you count 64 bits. If it is only 10 here, then you count only 16 bits and so on. Same thing with the source address. Frame version is because the frame format has been changing, so this is the version number is here for the frame. Anyway, so this is the MAC frame format. Everything is straightforward. One thing I wanted you to notice is, and remember, is that the destination address is variable length. Source address is same way. The PAN IDs are variable length. They become variable length simply because either they are there or not there. Right? And then security is again another thing optional. And so because here the bits are, basically 127 bits is all you have, 127 bytes is all you have total. Every bit is important and every bit you can save is good. So basically that's why they have made so much variability. In high speed LAN, the design is slightly different. This is low speed. In high speed LANs, the bits are plenty. When you're running at 100 megabit or something like that, you don't care for a bit. And you put everything fixed because at that speed, you really want to move fast. Okay? You don't want to count bits and then find out where the address is. Right? At the low speed, this is totally opposite trade-off. You have enough time to count the bits, right? And you don't want to send the bits on the wire. So that's why you have variable fields. And that's the point I want to drive home. Is that clear now? Yeah.
Why would the PAN, I'm not sure, like, what's the situation when the PAN ID would be there and when would it not be there?
Oh, okay. So basically, the thing is, if you are using 64-bit address, you really don't need the PAN ID. That is clearly one situation, and there could be other situations for sure. If I want to talk to you and I have your 64-bit address and you have my 64-bit address, then I don't need to say which PAN we are talking it on. All right. Now, this was the summary of this. Basically, A2 2.15.4 has been around for a long time now. I think it started around 2003, or I think 3 was the first version. Now it is 13. So in 10 years, it has become quite complex. And so I said it runs at 2.4 gigahertz. That was a big simplification. Each actually runs at many different frequencies. Any country has any allocation, they have to design a standard. And so there is a standard there are two standards for 2.4 gigahertz. There is a standard for 915, then 868, and then 780, and then 950, and then, there are other modes. So there are many different PHYs. Each of these bands basically uses something similar. So in many cases, they use what we said before was the spread spectrum. And so there are chips. Right? So there is a bit rate. You take many bits, make a symbol, and then you take each symbol and make that into chips. Right? So for example, the first one, you have 250 kilobits, you divide by 4 bits per symbol, you get 16 symbols. Right? 16 symbols are converted you get 62.5 symbols, 1000 symbols per second. They are translated into 2000 kilo chips per second. So you can divide and see, I think it is 16. Is it 16? 32? It could be 32. So there are 32 chips per symbol. Right? And then chips are nothing but the bits, right? 01, 01, 01. You take them and you use QPSK to modulate them. QPSK only takes 2 bits to make the phase. Right? 4 phases. But this is not QPSK, this is OQPSK. So I have to explain to you what is OQPSK. I'm going to do that in the next few slides. But the idea is that this is the original and the most common PHY that is used. Then there are these other PHYs which have come in. And there are other modes which have come in. So I have to now explain to you so that you understand what are these new developments, such as PSS. This is a spread spectrum of a different kind, parallel spread spectrum. Of course, OPQPSK, UWB, Ultra-Wideband. So these are important developments, and I thought that I should basically explain them and not just skip them. We can very safely skip these stuff because most of the world runs on this. However, these things might be coming. And the reason they have been there is a demand for these is because 2.4 is very congested, and 2.4 doesn't go as far as some of these lower frequencies go. So you know about 700 megahertz, right? So these 915 and 780, and these are better than 2.4 in distance, right? And then UWB has some properties that we will see in a minute that make it suitable for going on your body area. Okay? So now the next part of this lecture class is about these special modulations. But one thing you should understand before I go there is that you take the bits, make the symbols, translate the symbols into chips, and then you use the modulation to put those chips on the sine waves. Right? Everybody understand that part? So if suppose somebody says, how do you get 250 kilobits, and how do you get whatever it is, but basically, so the idea is that you have to translate that into symbols. So 4 bits per symbol. Then from symbols you go to chips. So you take 32 bits per symbol. So each symbol becomes 32 bits. And then each of the 2 bits becomes a point in that modulation scheme. Okay? Alright, so how many different things we are going to talk about? We are going to talk about offset quadrature phase shift keying, OQPSK. And we already said that this is the modulation which is used with the direct sequence spread spectrum. And the reason they selected DSS rather than frequency hopping. So now here's another interesting thing I found, that the thinking philosophy between Bluetooth and 15 is just the opposite. They selected frequency hopping. These people selected DSS. And I can see the criticism in this community about frequency hopping, and of course they will criticize this. And that's why the two communities departed. Bluetooth is no longer part of 802.15. It started life as 802.15.1, but now it is no longer part of IEEE. So here they are saying that DSS is good because of the spread spectrum, because of the codes, they can quickly get to their the signal, settle it, and then start, so basically that saves them time and energy. Binary phase shift keying you already know, so I'm not going to talk about that. BPSK, that is straightforward. ASK is straightforward, amplitude shift keying. But what is important is parallel sequence spread spectrum. So we haven't talked about that spread spectrum. Parallel sequence spread spectrum. So I will talk about that. Then there is chirps spread spectrum. Chirp. Okay, so I kind of missed it here somewhere. One of them is chirp. Okay, spread spectrum, and that is used with differential quadrature phase shifting. And so we have talked about quadrature and we have talked about differential. Okay, and so I will not talk about that, but I will talk about chirp. Ultra-wideband, which is really totally different with burst position modulation. I will talk about that. Emery phase shift keying. So basically, this is a good name for basically phase shift keying, PSK. So we already know QPSK, which is M equal to 4, and you could similarly have 16 PSK and 32 PSK and 64 PSK, and that is called Emery phase shift keying. And then we have and then Gaussian phase shift keying, which we talked about last time, so I'm not going to talk about that. So let's see. So there are a few things that are new, and we will go one by one. Offset QPSK. In a normal QPSK, what you do is you take 2 bits and make that a phase. So this will be 45-degree phase will mean 1, 1, and 135 phase will mean 0, 0. So if you were to transmit from 1, 1 and after that 0, 0, your phase will go by 180 degree. And anytime there is a sudden change, whether it is in amplitude or whether in phase or whether it is in frequency, is bad. Okay, remember Gaussian frequency shift keying. If you have a sudden change in frequency, it's not good. So we said, okay, we'll have a smooth change in frequency. That is Gaussian. Similarly here, they came up with the idea that if you have to go 180 degree phase shift, that's not good. We should go slowly there. And so to do it slowly, what they do is they divide it into really one bit at a time. First they change the I and then they change the Q. Then they change the I and then they change the Q. I is this axis, Q is this axis. This is the sine theta, this is the cosine theta. So when you say 45 degrees, all you are saying is something times sine omega t plus same thing times cos omega t. So that is why it becomes 45 degrees. Same amplitude for both sine waves and cos wave. So here is what we are doing. So 1 1, we will do 1. This is sine wave, and this is 1 cos wave. Okay, but we will basically do it. So 1 sine wave, cos wave, 0 1. This is sine wave 0. See 180 degree, and then this is 1. This is 0. This is 1 0 0. 2 zeros in a row, and so on and so forth. Similarly, on the cos side, you have 1 1. This is 0, and so on and so forth. And then you add it up, and that's what you transmit on the wire. Now when you add it up, you will see that the maximum phase change at any point is 90 degrees, not 180 degree. Okay, and so this is basically the idea around OQPSK, and that's why it is used in many of these variations. OQPSK, 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 OQPSK. So let's see. Let's summarize this. Just the general idea here. General idea is that whenever you do amplitude shift keying or phase shift keying or frequency shift keying, in any of these, just sudden shifts are not good. So we want to smooth out those sudden shifts. And so this is one way to do for the phase shift keying. Okay? Any question about this? All right, spread spectrum. So the spread spectrum is very straightforward. Basically what you do is you take a code, and when you want to send a 1, there is a code for 1, and the opposite code is for 0. So you send those, and at the other end you correlate. You take your code, and whatever you receive, you correlate, and you get the best estimate. Okay, this is a 1 or a 0. So if you have 11 bits to decide whether it is 1 or 0, you have a very good chance of getting it right. Right, at 31 bits and whatever number of bits. So you take lots of chips and then you decide whether it is 1 or a 0. So that is what code direct sequence spread spectrum is, right? But chirp. Now what is chirp? Parallel. So the parallel thing is that you don't take just one code, you take many different codes. And you could have any number. Let's say you could have, you have 10 bit, let's say you have some number of bits of code length is one thing, which is L, but you could take any number of bits, any number of codes. And how do you get these codes? You get these codes by cyclic shifting them. So you take this sequence and then you cyclic shift them, and then you convert them from bipolar to unipolar. That is the important part, is that this is -1 + 1, and this one becomes 1 0, and there is a whole mathematical formula behind it. You take the k plus I mod L value of A, add 1 to it, and divide by 2. So if it is +1, if that value is +1, you will get +1. If it is -1, you will get a 0. So anyway, so you get these codes, and then you modulate the bits by these codes, add them up, and send it. Because now it is no longer, because you are adding some numbers, so there will be multi-level code. You could go very high, very low, and all that. All right. Now, so that's in some sense a negative, that you have too much variation here. But it turns out when you do the receiving part is very similar to the previous one, as if you didn't do any of this. Receiving part is basically you do the same correlation with A, with the original code, and you get the bits correctly. So the idea is, why do people do that? And they showed that this one basically is good for multipath. So it increases the resistance to multipath fading. And so this will be used only when there is a significant multipath. When do you think is a significant multipath? When the distance is large or small?
Small.
Hold on. If you have small distance, there cannot be significant multipath. If you go by speed of light, there you go like this, or you go by like this. Right? If it is distance is large, then this is a problem. So it is used in these frequencies, lower frequencies. These are designed for longer distances. Okay? And these are designed particularly at the request of the smart grid community, which wants to read the meters from very far. They don't want to come to 10 meters of the meter to read it. They want to read it from the street. That means very long distance, right? So if you're going to do that, you have multipath issues and you use PSS. Right? Multipath is basically signal goes directly or signal goes by reflection. Right? And the difference between the two is the multipath spread. And so for that we need PSS. And PSS is basically, if you can remember, I mean, you don't have to remember the formulas, but what you do is you just make cyclic, you take a code and you just turn the bits around and make them unipolar actually, and then you just add up and send this multi-valued code. On the other end, you get mathematically they have shown that basically at the other end doesn't make much difference. You get the same bits out by the same method. All right, so that is one spread spectrum. There is another spread spectrum called chirp spread spectrum. What is a chirp? Chirp is a signal whose frequency increases or decreases. Okay, if you were to look from, just turn it around, then it will be decreasing. So here you see the cycle is this shorter. So this signal, the frequency is going up. This is chirp. This is how many birds speak. This is how the whales speak. This is the sound that they make because the frequency of the sound keeps going up, right? And so this can be used, if you can somehow do this, this can be used for communication. And so what you do is signal is frequency modulated with frequency increasing or decreasing from min to max or max to min. That way the power is spread over the entire spectrum. So the advantage is that if you suppose you use this as a 1, now the 1 would have power at this frequency, at this frequency, at this frequency, at this frequency, this frequency. Every frequency there is a power. Right? So when you look at the power spectrum, it is everywhere. That is why it is called a spread spectrum. Right? The power is not at one point, it is everywhere. But this is chirp. Chirp because basically the frequency is changing. Okay? And so this could be a 1 and the 0 could be just the other way around. So this is chirp spread spectrum, is that you use the frequency increasing or decreasing as the code, as the way to indicate 0 or 1. All right. Now ultra-wideband. Now this is very different. Actually, I could have given a whole lecture on ultra-wideband because this is a technology that has a lot of interest by many people, and I have gotten many calls from different people about this, simply because we have some papers on our website on this. But this idea is important, so listen carefully. If you have a sine wave in time, what does it look like in the frequency domain?
There is one frequency, it will be like
Yeah, if it is one frequency, we'll look at impulse. Sine wave in time domain is an impulse in the frequency domain. Now just the opposite. An impulse in the time domain is what on the frequency domain? On the frequency domain, it's a constant, it's, every frequency is there. Okay? Actually, it doesn't stop anywhere. It goes from minus infinity to plus infinity. Well, I'm sorry, it doesn't go to minus. I don't think there's a minus frequency. So 0 through something 0 plus through plus infinity. Okay? So the idea is, if this is the case, then why don't we just send the impulses? And if we just send the impulses, then the power is not going to be too much. Because the thing is, if you send, let's say, 1 milliwatt here, impulse, this 1 milliwatt will be divided into infinite frequency, so the power level would be 0. Right? Very low power. So impulse in the time domain results in ultra-wide spectrum. Now this is an ultra-wide spectrum. It's very wide. In frequency domain, and actually looks like a white noise to other devices. And other devices will think that this is a noise, white noise, which is always there anyway. So some smart guys came up with this idea. And then FCC says, okay, it's okay, you can do this. So now let me tell you what. Basically, FCC allowed this in 2002. And the idea was that if you don't do anything, there is noise in the air. Right? There is minus 40 dBm is allowed. If your computer, you sit next to the computer, there is minus 40 dBm is emitting even where there is nothing is going on, right? So that is the noise level. Minus 41.3 dBm per megahertz. That is noise level. When you transmit something, then there is a power limit that as to how much more you can transmit and all that. But underneath this, nobody cares. So somebody said, can I use that please? If you don't care, can I transmit it in the allocated band? In the band where everybody else is already bought in $1 billion, but they don't know, can I transmit noise? Right? And so that's the idea. So basically, FCC rule restricted the maximum noise generated by wireless equipment to minus 40 dBm or 41.3 dBm per hertz, which is like 0.1 microwatt. But it is possible to generate sub-nanosecond pulses that have a spectrum below that level. Okay? And since they are sub-nanosecond, you can have millions of those and billions of those, so you can get 10 gigahertz. You can get gigabits using 10 gigahertz spectrum. Okay, at the noise level. So FCC approved this in 2002, and so now they can be used for a very high speed. Now this is for high speed, not low speed. For very high speed over short distances. And interesting thing is, they can go through the trees and through the underground and through the walls and so on and so forth, because they are like pulse, they are impulse. If you put a hammer here, you can hear the other side, right? So that's the kind of effect it is that you can see inside the walls, and so they can be, and they are very precise in positioning. So if you send a pulse, when it comes back, you can figure out how far did it go. So they are very good for tracking high value assets. So if you put some diamond behind the wall, you can monitor it from here and see if the diamond is still there. Okay, because if it moves by a centimeter, the UWB will tell you that it is not there. So it has many applications, and this is how it looks like. This is a pulse, this is a pulse, this is a positive pulse, this is negative pulse, and so on and so forth. Right? And then position is also possible. This could be a 1, this could be a 0, or so sub-nanosecond pulses are sent many million times per second. became feasible with high-speed switching semiconductor devices. Previously, we could not generate these pulses, but now we can. Pulse width is only 25 to 400 picoseconds. And these pulses may be position, amplitude, or polarity modulated. So position is clear that if the pulse is in the beginning, it is 0, 0. If it is here, it is 1, 0. If it is here, it is 1, 1, and so on and so forth. You could just modulate it depending upon the position. It could be amplitude modulated. If it is this big, that big, so on and so forth. Generally, they won't go multi-bit, but I mean, I'm just telling you that basically you could have 1 or 0. Amplitude or polarity modulated, positive or negative. And then, if you have 0.25 nanosecond impulse, or basically this is the bit we are talking about, this whole thing, which is not a pulse. Basically, pulse is only picosecond. Nanosecond is between the pulses. So if you have 0.25 nanosecond per pulse, you get 4 billion pulses per second, and that could become hundreds of megabits, several gigabits, 4 gigabits up to 4 gigabits, right? I mean, it could be, if even if you get 1/4 of that, you get 1 gigabit. So everybody was very excited about UWB. There was a time, and so 15.3 started working on it, 15.4 started working on it, and many other people started working on it. And 15.4 finally settled on something that we are going to talk about in the next slide. However, 15.3 gave up. 15.3, the people fought with each other. They got out of IEEE. They went to other places, and they never succeeded. Okay, so that is dead. In the previous time when I taught this lecture, wireless, we talked about 15.3 and we talked about those possibilities, but 4 years later they're not here. But now what is here is this one. But before I go into the 15.4, one thing you notice is very low energy consumption. So you get lots of, you get very low watts per megabit. Line of sight is not required, passes through the walls, passes through your body. And so sub-centimeter resolution allows precise motion detection. Pulse width much smaller than the path delay. So that is another thing, is that since these are very narrow pulses, if you get multi-path delay, you can very easily figure it out, because one pulse can become multiple pulses and you will know that this is the path delay. So it's very easy to resolve multi-path, and then it is very difficult to intercept. So that's another thing, is everything is noise. When somebody looks, all they see is noise. Right? So very difficult to intercept. All digital logic. So low cost chips and very small size. Alright, so there's a lot of activity in UWB, particularly in the healthcare area. And you can imagine why healthcare area, because with so little noise you can put it on your body, as opposed to Bluetooth or Wi-Fi or anything like that, right? I mean, it's really bad that we have to have Bluetooth, Wi-Fi computer next to us whole day. But this is actually okay. I mean, looks like okay, at least now. Okay. So there are different methods of doing UWB, but one method, which is called DSUWB, direct sequence UWB, direct sequence is the spread spectrum, is that you take some bits and then convert them into chips, CDMA, and take those chips and convert them into pulses. All right. And why do you need to convert them? Because if you convert them, then basically you can make some information out of the noise. Basically, you do the correlation, and if the correlation says, yeah, this is a 1, 10 bits or 11 bits or 100 bits, say it is 1, you are happy. Right? So you just don't take one bit and you transmit it as a pulse. You take a code and transmit it as a pulse. And this is the scheme that is used in 802.15.4, and this is good for body area network. Yeah.
I just don't understand how the receiver will be able to detect this signal, because it's on a very broad frequency.
Yeah, right, exactly. So what happens is the this requires a little more than, more electrical engineering than I can tell you. But the digital logic, basically digital logic, somehow, and I'm sure this is some kind of digital signal processing, DSPs, which are designed, which take this signal and somehow make out the pulses. Once you get the pulses, then you get the code and then you do the rest of it. But your question is valid. I don't exactly know as to how they can convert that noise back into the signal. It's easy to see how the signal can convert into noise, but how you get back from there to here. All right. So that is all PHYs. So let's see. Any question about any of these PHYs? And I will just put this slide back so that you know which PHYs we talked about. We talked about offset quadrature phase shift keying, where we take 1 bit at a time and rather 180 degree phase shift. We have 90 degree phase shift. Then we talked about chirp. Chirp is where we move the frequency slowly up and do the spread spectrum. Then we talked about ultra-wideband parallel sequence spread spectrum, where we take a code and make many codes by cyclic shift. Then we talked about ultra-wideband, where we create a noise. And then we have Emery phase shift keying, which we didn't talk about actually. Basically, all it is an extension of QPSK. M equal to 4, we already know. So now you can have PSK 16, just like QAM 16, QAM 64, you have PSK 16, PSK 64, etc., etc. And Gaussian we talked about last time, where phase shift is not jump, but by smoothly Gaussian. All right. So after that, we come to some new developments. And that is that, so there is a new standard 4E, which is an extension, and it has many different new things which have come in. And I wasn't sure how much time to spend because we are actually running low on time right now. So I first made the slide on each of these things and then I deleted them actually. So I just want to give you a simple idea. Is that first thing, there are 5 or 6 things that they have added recently. Now these are recent things, so they're not in the products yet, and time will tell how many of these are good ideas and not good ideas. But they have added a low latency deterministic operation. So there are some applications which want deterministic operation. They can't stand CSMA. And they want low latency. So they do want that microsecond accuracy or millisecond accuracy. When they want it then. And so for that, you really need something. So they have pre-assigned slots. Basically, there are slots, and then slot number 1 is yours. Whether you speak or not, it's gone. But if you speak, you get it right on time. Second thing is channel adaptation. Is that if you are going to use just one channel, it may be good for you because you are here, but it may not be good for him because he's there and somebody else is speaking on the same channel. Now the distance has gone up from 10 meters to 100 meters. So the channels are not the same for everybody. Coordinator may like this channel, but the other guy may like the other channel. So different channels are allowed. Okay. Time slotted channel hopping is that the higher layers will tell you that, okay, the next cycle, you go on channel 1, you go on channel 2, you go on channel 3, you go on channel 4. So there will be many parallel transmissions, and everybody knows what channel they're coming in and coming out. So this is nothing to do with the 15.4. Somebody will tell you right away that this is the channel you want to listen on. And this is good for industrial environment. Each device can select its listening channel. Fourth mode is that you could say, well, I want to listen only on channel 5, just fixed channel. And you want to speak only on channel, well, if I want to listen on channel 5, you have to speak on channel 5. But you could say your listening channel. You could say, well, I want to listen only on 10. So the transmitting channel has to be variable. But The reason it works is because there are many devices which never speak or which never listen. Okay. So there are devices which are transmit only or receive only. Right? So for those devices, it's good to have just one channel and be done with it. So listening channel. Transmission and receiver coordinate their cycles, very low duty cycles. So here's the thing, if suppose we are going to wake up every day, why do all this CSMA and beaconing and whatnot? So we could decide that every morning, 6 a.m., I will call you and you listen to me. That's it. So for long, low duty cycle stuff, you could just talk to your partner and decide when you are going to wake up and then go to sleep and then come back up. So that is a new method. Transmit only when requested by the receiver. And the second thing is the receiver is such that it is always sleeping. So if you want to transmit to it, you just wait until the receiver comes up and says, okay, send me now. So right now this is possible to do with the coordinator. Coordinator always stores your stuff. When you wake up, you tell the coordinator, okay, I am up, please give me my messages. But now you can do it with any node. So the node will wait, and when you say I want it, so here there is asymmetry in the sense that the node that is waiting probably has electric power, and the node that is sleeping is running on a cell battery, right? So that's why they say that you just transmit only when the receiver says I am ready to receive. So these are the 6 changes which have come in from 4E. Any question about this 6? That brings us to the end of the lecture today. IoT, fueled initially by smart grid, is resulting in several competing protocols. Bluetooth Smart, Zigbee Smart, and so on and so forth. And so we want to learn about all that. So IoT is very important. So here is a kind of decision I have to make, is that where to spend most of the time. There are so many new things happening in wireless. We cannot cover it in one semester. So I have decided that I will want to spend a little bit more time on IoT this time than other times. So you might hear a little bit more. And so that is what it is that we will spend on IoT. 82.15.4 is a low data rate personal area network, and PHY and MAC, which is used by many IoT protocols. So we will talk about them next time, Zigbee and wireless hardware, etc. But we now know 15.4 at least. 15.4 uses full function and reduced function devices. So that full function can act as a coordinator. It allows a star, mesh, and cluster topology. Uses slotted and unslotted, both modes. And it uses CSMA-CA, supports guaranteed transmission as well. So there are lots of options. Then the newer PHYs use chirp spread spectrum, parallel spread spectrum, and UWB. Now UWB allows transmission with very low average power spread over a large band. So UWB is something that is very much of great interest to medical community. All right. Reading list, there is a whole book. Actually not a whole book. The first chapter is on this 15.4. And this one talks about PSS, and this one talks about CSS. There is plenty on Wikipedia, not too much, but yeah, plenty. That's it.